to this VLSI series of lectures. I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering, IARE. Today, I am going to discuss implementation strategies for full custom and, if time permits, for semi-custom design also. So, ASIC, it is an acronym for Application Specific Integrated Circuit. So, as the name indicates, it is a non-standard integrated circuit that is meant for a specific application. And generally, this design is undertaken for a product that has a large production run. And this may contain a very large part of electronics needed on a single integrated circuit. So, examples of ASIC chip are for a satellite and a chip designed to handle the interface between the memory and a microprocessor, for a computer, or a chip containing microprocessor itself together with other interfacing logic. The classification of ASIC is like this. ASIC is classified into three categories: full custom, semi-custom, and programmable logics. The semi-custom is further divided into three categories: standard cell-based, gate array-based. So, semi-custom is divided into two categories: standard cell-based and gate array-based. Gate array-based is further divided into two categories: channeled gate array, channel-less gate array, and structured gate array. Programmable logic, it is divided into two categories: PLDs and FPGAs. FPGA stands for Field Programmable Gate Array. Now let us discuss about the full custom ASICs. So full custom ASIC, this includes some logic cells that are customized and all mask layers are customized. So all the design is done by the designer. So the designer, he does the work from scratch. He does not take standard cells or standard libraries from anywhere. He does everything on his own. And a microprocessor, it is an example of a full custom design. Because the designer does everything on his own, it requires a lot of time. So he spends a lot of hours squeezing the most out of every last square micron of microprocessor chip space by hand. And customizing all the IC features in this way, it allows the designers to include analog circuits or memory cells or mechanical structures on an IC. So, full custom ICs are most expensive to manufacture and to design. They are not only most expensive to manufacture and design, but they take a lot of time for the design. So, the time to market also is very high. So, just now I mentioned that the manufacturing lead time is high and it is typically 8 weeks for a full custom IC. It is approximately 8 weeks for a full custom IC. So, these specialized full custom ICs, they are often intended for very specific application and like space or military applications. So, we call them for full custom ICs. So, in a full custom ASIC, the designer designs some or all of the logic cell circuits layouts specifically. So, this means that the designer avoids copying from other standard libraries. So, the designer, he avoids using pre-tested or pre-characterized or proven cells for all or part of the design. He doesn't believe in libraries from other places. He does everything on his own, including the MOSFET design, the logic designs, or data path system design. Everything he does on his own, as per his own requirement. So this might be because existing cell libraries are not fast enough, or the logic cells are not small enough, or they consume too much of power. So because of that, he does everything on his own. So in full custom ASICs, one has to use this design if the technology is new or it is so specialized that there are no existing resources available. Because the ASIC is so specialized and it is because it is very innovative, and the existing cell libraries or the circuits, they are not suitable, so they must be specially designed. And another reason for full custom ASIC design is because of the problems with these special parts of ASIC. And the growing member of this family, it is nowadays is the mixed or analog digital ASIC. So this is the full custom ASIC. And ASICs for which all the logic cells are pre-designed or some of the mask layers are customized, they are called as semi-custom ASICs. So another category of application-specific integrated circuits is semi-custom ASICs. So here, all of the logic cells are pre-designed and some of the mask layers are customized. That means cell libraries are pre-designed, but the interconnections between the cell libraries is done by the customer as per the specific product specifications and layout. So he takes all the cells from other resources and only he does the interconnection. He does only the integration. So using the pre-designed cells from a cell library makes the designer life much easier because he is taking the proven libraries from other sources. He is doing only the assembly. So the design is simpler and the design is done fast. So the design time is reduced and the time to market also is reduced. And there are two types of semi-custom ASICs: standard cell based ASICs and gate array based ASICs. One is the standard cell based ASICs and the next one is gate array based ASICs. Now let us discuss about the standard cell based ASICs. So this is also called as CBIC or a cell based ASIC. So this uses the pre-designed logic cells like AND gates, OR gates, multiplexers, flip-flops, encoders, decoders. So these are the standard cells and these are applied, or one can apply the term CBIC to any AC that uses these cells, but is generally accepted that a cell-based ASIC or CBIC means a standard cell-based ASIC. So here the standard cell areas in a CBIC, they are built of rows of standard cells like built of bricks. So the bricks are of same shape. So like that, the standard cells are taken and the interconnection is carried out. And the standard cell areas may be used in combination with other modules like microcontrollers or even microprocessors known as mega cells. So these mega cells are also called as mega functions, full custom blocks or system level macros or fixed blocks, cores or functional standard blocks. Now this is the structure of standard cell. A cell-based ASIC is also called as CBIC, or this is the example of semi-custom ASIC. So here you see these are the fixed blocks 2, 3, 4, 5. So these can be AND gates, OR gates, microprocessors or microcontrollers, which are taken from the standard libraries. And this is the standard cell area. So the interconnection is done between these modules as per the specifications of the product which is to be designed. And these are all the input output pins. What you are seeing here, these are all the input output pins, and the connection is carried out as per the requirement of the customer. So this is the layout of CBIC. So in semi-custom ASICs, the designer defines only the placement of standard cells and the interconnect in a CBIC. He takes the standard cells and only he defines where to place these standard cells in the layout. And he also does the interconnection work. So these standard cells can be placed anywhere on the chip. That means all the mask layers of a CBIC, they are customized. They have to be done separately and are unique to a particular product or for a particular customer. So what is the advantage of CBIC? The designers, they save a lot of time, money and reduce risk by using a pre-designed, pre-tested, pre-characterized or proven standard cell library. So in addition, each standard cell can be optimized individually. So during the design of the cell library of each and every transistor, in every standard cell can be chosen to maximize speed or minimize the area. So depending upon the requirements of speed and area specifications, he can choose the cells from the libraries. What are the disadvantages? The disadvantages are the time or expense of designing or buying the standard cell library, because he is taking pre-tested, pre-designed libraries elsewhere. He has to buy those cells and it involves money, and also the time needed to fabricate all layers of the ASIC for each new design. Now let us come to the gate array based ASICs. So gate array based ASICs is also called as GA. So here the predefined pattern of transistors on a gate array is called as the base array, and the smallest element that is replicated to make the base array is called as the cell. So only here the top layers are customized. So the top few layers which define the interconnection between these cells are done by the designer. And to distinguish this type of gate array from other types of gate array, it is also called as masked gate array. So here the designer chooses from a gate array library of pre-designed and pre-characterized logic cells. These gate arrays, they are further subdivided into three categories: channeled gate arrays, channelless gate arrays, and structured gate arrays. These are the three types of gate array based ASICs. So these logic cells in gate array library, they are also called as macros. So the reason for this is that the base cell layout is the same for each logic cell. So if you take a channel gate array, there is only one type of logic cell for the whole chip. Only the interconnect is customized. There is no diversity. Either they are all same type, they are all of same type, only the interconnection is customized. Now let us discuss one by one the channel gate array, the channelless gate array, and the structured gate array. Now this is the channeled gate arrays. In channeled gate arrays, you have rows of cells, and these array of cells are separated by gap, and the gap between rows is fixed in height, and the gaps between the arrays, it is used for interconnection. So the channeled gate array was the first to be developed, and the channeled gate array space left between rows of transistors is used for wiring. So here you see this is the array of cells, this is an array of cells, and this is a gap, and this gap is used for interconnect. So the difference is that the interconnect between rows of cells, it is fixed in height in a channeled gate array. So when you have several channels like this, this is array, this is another array of logic cells, this is another array of logic cells. So this gap is fixed between the channels, and this is used for interconnection. So the space between rows of cells may be adjusted in another type, that is in CBAC. But here in channel gate arrays, the gap is fixed. In CBAC also you may have you have gate arrays, but the gap is adjustable. But here the gap is fixed in channel gate arrays. Now let us come to channelless gate array. In channelless gate array, there is no channel. So you have only the whole area you have cells. And how the interconnection is done? See, this is the whole area. This area, it has all cells, and the interconnection between the cells is done on the top layers. So when you are doing interconnection between any two cells, on the top layer, in the area beneath the layer, those transistors, they are not used for wiring. They are left unused. So the key difference between a channelless gate array and channel gate array is there are no predefined areas left aside for routing in channelless gate array. So we route over the top of the gate array devices. So here you have top mask layer, here this is the bottom mask layer. So this top and bottom mask layer, this area is used for the interconnections. So we can do this because we customize the contact layer that defines the connections between metal 1 and the first layer of the metal and the transistors. So in channelless gate area, the interconnect is customized, and the interconnect uses predefined spaces between rows of base cells. The manufacturing lead time is around 2 days to 2 weeks. And when we use the area of transistors, as I have mentioned just now, for routing in a channelless array, we do not make any contacts to the devices which lie underneath. So we simply leave the transistors unused. So this is about the channelless gate array. So in channelless gate array, because there is no channel, you get maximum number of transistors. The density is more. Now again, let us discuss about the differences between channelless and channeled gate array. The basic difference is in channelless gate array, there are no predefined areas set aside for routing in channelless gate array, but in channeled gate array, we have areas which are set aside for interconnect, and that area has a fixed height. So we use the area of transistors for routing in a channelless gate array, but we do not make any contacts to the devices lying underneath. We simply leave the transistors unused. And we get more package density in channelless gate array, and the channelless gate array also is called as sea of gates. It's also called as sea of gates. So the logic density, that means the amount of logic that can be implemented in a given silicon area, is very high for a channelless gate array compared to channeled gate array, because of the difference in structure between the two types of arrays. So the difference occurs because the contact mask is customized in a channelless gate array, but is not usually customized in the channel gate array. See, if you have a top layer and bottom layer, the top layer and bottom layer is not is having a fixed configuration in channel gate array, and mostly that is used for VDD, VSS, and global clock supplies and the necessary connections. So it is fixed. But in channelless gate array, you are making the interconnections to the cells using these top two layers. So it is customized. So in channelless gate array, you have denser cells. So customizing the contact layer in channelless gate array, it allows us to increase the density of gate array cells because we can route over the top of the unused contact sites. So there is a difference between channelless and channeled gate array. Now structured gate array. See, in structured gate array, it has an array of basic cells and it has an embedded block. This embedded block can be a microprocessor or a microcontroller, and in the remaining area, either you have a channel gate array or channelless gate array. So here you have channel or channelless gate arrays. And these are the input-output pins. These are the input-output pins. So what are the features of structured gate array? The interconnect is customized. The custom blocks we have, like microprocessor or microcontroller. And the manufacturing lead time is between 2 days and 2 weeks. And embedded array, it gives the improved area efficiency, and also it has increased performance of a CBAC but at a lower cost. And it has faster turnaround time. The disadvantage of embedded gate array is that the embedded function is fixed. You cannot change the function of the embedded block. And for example, if an embedded gate array contains an area set aside for a 32 kilobit memory, but we need only a 16K bit memory, then we may have to waste half of the embedded memory function. So however, still this may still be more efficient or cheaper than implementing a 32 kilobit memory using macros in SOG array. SOG stands for C of gates. So we have discussed about the ASICs. So ASIC basically contains full custom design and semi-custom design. And semi-custom design, we have other classifications, and other classification is programmable gate array. Now let us discuss about the VLSI design process. So as the design complexity is increasing because of the increased size and complexity, and the fabrication technology also is improving. So because of all these things, the design complexity is increasing. The design complexity is increasing rapidly because of increased size and complexity, and because of improvements in the fabrication technology. So earlier the design was carried out by hand when the circuit complexity was less, when the sizes were very limited. Earlier we had only 100 to 1000 gates in a chip, but today we are in the era of billions of gates. The same chip we are able to accommodate billions of gates. So it is not possible to do the design by hand. So we have to go for CAD tools. So when we go for design using CAD tools, we can design chips of very high densities. And the important metrics of chip design are area, speed, and energy consumption. And these specifications have conflicting requirements. Suppose if you aim at reducing the area, probably the speed or energy consumption may become more, or if you want to reduce the energy consumption, probably area may become more. So it is difficult to reduce all these three specifications. So if you increase, if you improve one specification, another metric may get deteriorated. So these have the conflicting requirements. So what is the present trend? The present trend is to standardize the design flow. So the emphasis is on the low power design with increased performance. Why we go for low power design? Because nowadays most of the systems are battery based. So when the systems are drawing power from the battery, it's always advisable to aim at low power so that you get maximum backup time. Now, the technology is going rapidly at a very high speed in VLSI. Now, in CMOS technology, we are almost reaching the area of 22 nanometers. And for to improve the densities further, the source and drain areas, they are stacked vertically, and a FinFET technology has come up very fast. Now, most of the modern processors, they use FinFET technology, and the technology is 14 nanometers. The next upcoming technology is quantum. Of course, this is not has coming to the implementation, but the next technology is going to be quantum. So whatever chip you design, the VLSI design flow has basically these steps. So the VLSI design flow, it is a procedure to realize the design idea to actual realization on the silicon chip, and this has many steps. Like you have to provide the specification, then you have to go for synthesis, then simulation, then layout, then testability analysis, and many more. So these are the steps which are there in any VLSI design flow. Because the manual design is not possible, because the modern chip contains billions of gates, we have to use the CAD tools. So the CAD tools, they are based on the hardware description language. So these hardware description languages, they provide formats for representing the outputs of various design steps. And a CAD tool basically transforms the HDL input, the hardware differential language input, to HDL output, which contains a more detailed information about the hardware. So first is the behavioral level to register transfer level, then from RTL level to gate level, then from gate level to transistor level, then from transistor level to layout level. So these are the steps of the VLSI design flow. Now, two important HDLs, hardware differential languages, are Verilog and VHDLs. And these designs are created typically using HDLs, and which they get transformed from one level of abstraction to the next as the design flow progresses. So this is the simplistic view of VLSI design flow. First is the design idea. Next we go for the behavioral design. Then follows the data path design. Then the logic design, followed by the physical design, manufacturing, and finally you get the chip. So behavioral design, it basically involves a flow graph or pseudocode, and pseudocode is written using Verilog or VHDL. Then we go for data path design. So here you get the design in terms of registers or gates or multiplexers or encoders, etc., etc. Then you go for logic design. The logic design, it consists of gates, and gates, OR gates, NAND gates, NOR gates, exclusive OR gates, like that. Then you go for the physical design. In physical design, the actual transistor layout is done. Then we go for manufacturing. So this is the simplistic view of VLSI design flow. Now let us discuss about the design flow in more detail. What is a behavioral design? So here we define the functionality of the design in terms of its behavior. And there are various ways of specifying the behavior. You can express it using a Boolean function, or you can express it by a finite state machine, or you can mention using high level algorithm. You can say if A is equal to B, then L is equal to M. Like that, you can express it using a C language, or you can express it using a truth table. So once you include this code in the Verilog, then it generates the necessary required hardware. So in behavioral design, the functionality of the design in terms of its behavior is mentioned. So this design needs to be synthesized into a more detailed specifications for hardware realization. Next is the data path design. So here, this generates a netlist of register transfer level components like registers, adders, multipliers, multiplexers, etc. So a netlist is a directed graph where the vertices indicates the components and the edges indicates the interconnections. Suppose you can say these are the vertices, say adder. This is adder, and let us say this is encoder. This is another mux, and this is some NAND gate. So these are all the vertices, and this is the connection between these components. So these are the nets. So the netlist, it is a directed graph where the vertices indicate the components and the edges indicate the interconnections. And a netlist specification is also called as the structural design. So the netlist may be specified at various levels, where the components may be the functional modules or gates or transistors, and it is systematically transformed one level to the next level. That means it is converted to logic level, from logic level to gate level, from gate level to the transistor level, actual physical layout. Now next comes the logic design. So in logic design, we generate a netlist of gates or flip-flops or standard cells. What is a standard cell? It is a pre-designed circuit module at the layout level. And there are various logic optimization techniques that are used to obtain a cost-effective design. And of course, here we have a conflicting requirements of optimization, like you cannot optimize area, power consumption, speed at the same time. So there are conflicting requirements during optimization. Now comes the physical design and manufacturing. Here, generate the final layout that can be sent for fabrication. So the final layout is to be given to the fabrication house for the chip manufacturing. So this layout contains a large number of regular geometric shapes corresponding to different fabrication layers. So alternatively, the final target, it can be a field programmable gate array where the technology mapping from gate level to the netlist is used. And FPGA, it can be programmed in the field. So you have much greater flexibility in FPGA, but the disadvantage is less speed. The speed is less. There is a disadvantage. So the other steps in the design flow are simulation for verification at various levels, logic level, switch level, and circuit level, and formal verification used to verify the designs through formal techniques. Another important step is testability analysis and test pattern generation. So this comes under the class of DFT. DFT is design for testability. Design for testability. So that means The chip can be tested by itself by including the features like BIST. Okay, in BIST, the test pattern is generated inside the chip itself. So these are all the various steps in VLSI design flow. So we have discussed in detail the important characteristics of full custom design, semi-custom design, and also we have discussed about the important steps in VLSI design flow. With this, I conclude today's session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.